Okay, this is just a edit because the audio didn't actually record the first time I did this, and since then I've switched operating systems and it's a pain in the ass to switch back over again. But I made a recording earlier today of my CuboBot, as I have done previously. This version is a much later stage and it's nearing completion essentially. And what it does is actually displays the correct behavior without any sort of issues or any sort of I wouldn't say temperamental, but without any sort of achievements, unmerited achievements essentially. So whereas I've had versions before where the CuboBot on the right here would simply, for some reason, have enough strength to simply power up straight up the hill, and all it would learn by the end of it is that if it just goes straight forward, it could solve it. This version, if I display it, while consistency is not its strong point, as by the end of this has only achieved a 35 to 37%, actually achieved about a 38% success rate. You should be able to see that while obviously it can't do it up the hill straight up, as it shouldn't be able to. You can get close, but it's not good enough. You can see that it has to do a small backward step up the previous hill in order to gain momentum, which is the exact behavior we want. So while in terms of the results it doesn't reflect a perfectly good model, the desired behavior was quite clearly there, and in later episodes it really does try to implement that method. The only downsides I had was my code on the left hand side here. The epsilon value, which is the rate, which is the chance of a random action being chosen instead of a manual or model based choice being made, was quite high by this point, and this is about 2/3 of the way through the simulation. So a new version would have to be made with a slightly lower value, which I plan on doing before this is all done and dusted. But yeah, I wasn't aiming to actually solve the problem in this. It would be great if I can, and it would be great to write that up. But the ultimate aim of this project was to show that you can bring these classical AI problems into a more realistic setting, more so than the abstract version, while not necessarily taking them straight into the real world. The real world has so many flaws in it and so many issues in terms of training. It's a lot more hassle than it's probably worth. These simulations in a physics environment with 3D graphics and 3D physics going on is a very nice halfway house where, while it's not a true representation of the world, it's a very good imitation of one. One where you can see the real, it's not necessarily realistic, but you can see the realism in it, which is very good. As you can see on the left hand side, my previous recordings going through the reward system and stuff like that, and the various graphings I did. If we go through to, where is it? Oh, we'll run this through and just, oh, there we go. There's the reward system. So on this top two lines here is the current distance greater than previous distance, and current distance greater than the initial distance, and previous distance greater than the initial distance. So what this basically means is the robot going up the previous hill? If yes, is it consistently going up the previous hill? So was its last step also going up the previous hill? If yes, and then check, see, okay, was the previous distance also behind the initial starting point, which is where this origin point is here? If they're all three yeses, it basically shows that yes, we are consistently we are reversing up the previous hill. We will get a small reward for it. Now on the other side, we do the same thing again, but obviously if we're going up the bigger of the two hills, are we going up the bigger of the two hills consistently, as in motion after motion? Yes, yes, yes. Then we give it another reward. This doesn't give it, this is only a reward to incentivize behavior, not to incentivize correct use of the behavior. So all this does is eliminate any sort of stuttering that happens on the ramps. It doesn't necessarily cause it to actually succeed. Where I hope it causes it to succeed is the second if statement down here, which is if done, if failed, or else. So if done, so we've reached the top of the left hand ramp here, we give it a reward of 10,000. if for whatever reason we failed, and in this case a failure is simply a falling out of bounds error. So if we jump over to the right, jump over to the left, or fling all the way backwards, then we count that as a fail. We want to maintain, within the environment. Then we simply give it a reward of 10,000, and this is also just a method of desincentivizing bad behavior, and also it's just a quick reset method without any punishment, without any sort of cost attached to it really. Otherwise, if we're just doing a normal action and nothing catastrophic or amazing has happened, then we simply do a negative 10 reward, which is pretty straightforward. These are mostly the standard things. This is just incentivizing some of the minor behaviors to reduce some of the instability within the previous models I've had. Now the model itself, I've been following on a GitHub page. The general idea of it anyway. I mean, obviously it doesn't work for this sort of environment. It works for the OpenAI Gym 2D model, so really it's not very practical for this at all. But I've had to do some I've had to do some adaptation to it to make it work on this, which has worked out so far, I seem to think. As you can see, it doesn't always get it right. Sometimes it does still go backwards and fling itself off. And then sometimes you get weird physics like that, which suddenly spins on the spot. Still solves it, so I guess, if it works, it works, but the problem with these physics environment is it gives you only partial control over what all the variables are. So I can give it friction, but I can't give it friction specifically. I can't say give it traction or grip on the wheels. I can't do textures or anything, so I can't say this is a rough texture, which would a non-smooth texture, which would give it more grip. But for the whole, it works well. This is in the ODE format, by the way, not the Newton engine. I found the Newton engine to be very good, but also, one, very slow, because it takes almost 10 times the calculations more than ODE does for other reasons I don't understand. Two, it's still in a developmental stage, so I can't really guarantee it's the results. As obviously if it's experimental, it's a bit weird to be using, and if there are any bugs I can't be sure whether it's my fault or whether it's the engine's fault. So it's a good engine, and once they have a more stable and an implemented version along with Pirate, beefing up its usability a bit more in terms of more fine-tuning of the controls and access into the CoppeliaSim environment, I think would be great, but until then I can't really touch it. You can only sort of play around with it. You can use it if you want, but I wouldn't necessarily use it as anything substantial beyond a proof of concept that it works. So as you can see on the car environment class, on the left hand side again, we just have all the sort of values you could possibly get, and I've taken. I don't necessarily use all of them. Some of this is all legacy code which I need to get rid of before I hand it in. But you can get velocity, you can get time step, the time step of the environment, the current time of the environment compared to the previous time, the current position in terms of grid coordinates, because bear in mind it's an XYZ coordinate system, so anything you have to work out via that. Now agent get velocity, it actually returns a vector value, which I didn't find useful because it gives you a vector and doesn't necessarily give you speed, and speed is just more intuitive to understand. So what I've ended up doing in, as you can see in the get state class, just put a bit of a function down here, is actually I did a simplistic version myself of getting the agent speed, which is simply getting the distance from where it currently was to where it previously was, and then dividing that by the time difference as well, which in this case is usually a 0.05 time step simulation thing. So essentially you're doing distance over 0.05, which gets you the rough speed per tick, which is great because that's all you really need. Obviously if this is the real world, you might want to have that work a bit, more realistically in terms of actual time rather than sort of simulated time, but it does the job, and as far as I can tell it hasn't had any negative impact, and because it's relative to the environment it should be fine. It may not be the most accurate calculation there, but for me, it adds some clarity and some ease of use and ease of visibility of what the actual calculations are going on in it, as opposed to working with vectors, which I wasn't really comfortable with doing because it's a three-dimensional vector with a x vector, a y vector, and a z vector, and I didn't really know what to do with those in terms of working out what the total distance or speed was, so it wasn't really useful. Yeah, so I'll let this run a little bit longer, but what you can see is, I will say in later versions this got more consistent. I'm hoping another experiment I run later is one with a slightly lower epsilon and maybe a slightly increased friction, but I haven't quite decided on that because the friction seems to be working well, and I don't necessarily see the point in increasing the friction beyond just because you can. More so than a proof of concept of look what I can change. I mean, you can explore CoppeliaSim for yourself and see what the engine you can change and engine settings and stuff like that, which is all very straightforward and stuff. But yeah, so you can see some of the failed attempts there, some of the successful attempts on the right. You can see that's the step action I'm highlighting in the recording, which is simply a case of the environment will only run as you give it a step command. Meaning you can do all the calculations safely without having the simulation run on top of it, causing errors because of erroneous positions or stuff like being recorded. And you can see there the model, while unsuccessful, actually displayed perfectly the correct behavior. It just slightly may have missed one or two minor steps which caused it to kill its momentum off ever so slightly towards the fail. So maybe it didn't commit hard enough. So, and then you see like that again. It's perfectly the correct behavior, which is exactly what we want. It just doesn't necessarily solve the problem, but results can be the actual graphs, the results that come out of this are a little misleading because it doesn't necessarily reflect how well the agent performed visually. Numbers aren't everything, I'm afraid, in these sort of cases. You actually have to have a visual confirmation that it's doing the right thing. Otherwise, if it was purely numbers, then I'd simply have my old version where it simply powered up the hill constantly. I wouldn't be aware, but I'd claim it as a massive success until someone actually looked at it and realised I was horrifically wrong. But yeah, it's good. I like it. The model itself is relatively simplistic. It says it's a deep Q network. Honestly, it's pretty straightforward. You simply have a sample size of 2,000 steps ever iterated. Each step being obviously the position, the speed at the time, the chosen action, the reward that came out of it, and whether it was done, failed, succeeded. The model over time would try and change its weights to match those sort of input-output measurements. So essentially, the steps we're running here end up being the training data, which we then try and match our model to predict the correct outcomes from, in order to match the correct weights. And then eventually, as epsilon comes down, we then ask for it to predict what the correct action is given the scenario. And usually it actually does alright. Obviously you've got your standard variables of learning rate, how much you're going to discount the something or other. Sorry, it's a bit late and my memory's slowly dying on me, but you have the epsilon value, the minimum epsilon, the epsilon decay rate, which in this version was too high. 4 nines is just too high, whereas 2 nines ends up having it bottom out almost way too quickly. As you can see there, if I did a search for the made it sign, bear in mind this is just over 2/3 of the way through. About 30% ish, maybe 31% of those are successful iterations, which is great. Bear in mind I'm being me and saying extra, maybe 10 to 15 of those were extra. If you add an extra 10 to 15% on top of that, to a total of maybe 40 to 45% are correct behaviors, but not necessarily guaranteed a result, then I think that's really good so far. I think it's good. At this point, I'm just highlighting what I've already said, that the epsilon value is too high for this. But yeah, I'm not too sure what else to add. previous videos of mine should display the setup I did, some of the design issues and the various iterations I've gone through in making sure this works. I will say this CuboBot weighs a kilo, so unlike maybe Mars rovers where they weigh maybe 10 to 50 to 100 kilos, 10, 50, 100 kilos, it's a very lightweight model, more like a sort of robot you'd have in a lab or something, so not too bad. I'd class that as realistic enough. The key value here, the key values that get inputted are actually the torque values and the target velocity values of the little joints in the wheels there. So if you look very closely on the robot, on the right hand side there are little red dots in them. They're actually the joints, and the target and the torque is the strength of that turning power essentially. So how strong is that joint in terms of simple pulling power, so how strong does it make that wheel in order to get up the hill. I think this is set to a 3.5, maybe 4 value. Bear in mind it's a kilo, so it's pretty lightweight. So a small torque value is only needed to get up. Any higher, it becomes too easy. Any lower, it simply will never do it. So that's one of the things you've really got to test. But other than that, it can be a fixed value. I don't see a reason to have that as a thing. It has to modify itself. I think otherwise it just simply go too high and just win. Again, since the point of the thing is to demonstrate that it can solve with a swinging behavior, the use of momentum to carry it over the hill. The other value is target velocity, which is set to 1,000, and you might be thinking 1,000 is too high, and bear in mind this is 1,000 degrees a second, so how fast that little joint is rotating. It looks like I've gone over a little 10 minutes, so I'll cut it short a little bit in a minute. But yeah, so it's 1,000 degrees a second, which means that joint is spinning at is targeting a speed. Key point is targeting, it doesn't necessarily get to it. Targeting a rate of 1,000 cycles a second, or a time step, or whatever you want to call it. Very rarely will it ever achieve that, but any lower, say maybe 300, it does achieve that, and it ends up being too slow. Bear in mind a faster speed on a large wheel means the wheel will actually turn at a lesser rate than that, because obviously it's bigger. And the joint itself will not work on the floor, so you can't simply have the joints as the wheels. It has to be the wheels on top of the joints. But those combinations all together are what cause it to drive up the hill. And the way way my code translates what sort of direction we want to give it in is the choice of -1, 0, or 1, which then affects the target velocity to either -1,000, 0, or 1,000. -1,000 would force the robot to aim in a backwards direction. 0 will cause it to simply not do anything. And while it is toggleable to make it lock out, like some robots have, like mechanical lock, so they don't spin at all, this has been set so it should just roll. So there should be no momentum. It should be able to use the momentum to simply go with gravity, or go against its current momentum. Just how it works. And then obviously 1,000 is the forwards direction of the main hill. But yeah, hopefully this showed that numbers don't always mean the right thing, and sometimes you have to have a look a little bit behind the stage work and have a look backstage and see what's actually going on to really grasp whether it's doing the right thing or not, which in this case it's doing quite well. Again, I need to do some tweaking myself and see if I can bump those numbers a little bit, so you end up having a little more correlation. So before you look at the graphs and say, well, it did less than 50% correct, it's worse than chance, bear in mind that it's got 100 steps to choose from each time, and basically you have to say 30 of those consistently have to be the right set of motions to get right. And in terms of probability, that's pretty low. So the fact it's doing that well anyway is pretty good. Plus, it doesn't necessarily say that the correct behavior, obviously. It says 30% of the correct behavior equals the correct result, but it may be doing 50% the correct behavior, just not necessarily the correct result. So it's always useful looking at these, and I find these videos good little visual aids for those who are unaware of what is going on. Hopefully the next video I upload will be should be the end of maybe the test version of one of these models, which I hope to have running. But yeah, I'm on a time crunch now. I've got some writing to do, dissertation's nearly up. but I thought I'd put this stopgap in just so it's a bit more visual aid and I could put it in my dissertation. But yeah, there we go.